Hi, thanks for joining me for lecture 24. Here we're going to do more examples on momentum conservation, but this time we're going to be looking at cases where things are moving in more than one direction. So we'll have momentum conservation in 2 dimensions. Technically, we'll have it in any number of dimensions. So what we talk about here will generalize freely to 3 dimensions. We live in 3-dimensional space, or 4, 5, 6, 7 dimension if you lived in such a space. There are other applications for this kind of thinking with higher dimensions. But for our purposes, let's stick with 2, because I can actually draw 2 dimensions on a page. I can't draw anything else. 3 maybe a little bit, but it'd be hard to have accurate diagrams. So in 2D, and then that generalizes freely. So I'm going to look at 2 examples in particular. One where we put 2 objects, they collide, they stick together, and then one where actually I have 2 things collide and one of them breaks into smaller pieces. And so we'll analyze that. And the key insight, the key to solving problems involving momentum conservation in more than one dimension is that you have to look at the individual components of the momentum. So for each dimension you have one momentum conservation equation. Momentum in the x direction, momentum in the y direction. For each of those, separately, you do what you know to do for one-dimensional momentum conservation problems. So let's see what it looks like. So here's my first situation. I imagine 2 blobs. I don't really care what collides, right? It's all the same. Let's say just 2 blobs of some kind of goo. They collide as shown, and they stick together. So we see here there's 5 kilogram block going 3 meters per second to the right, and a 3 kilogram block going 4 meters per second at an angle that's 30 degrees from the I guess the vertical, or maybe from north. It doesn't really matter. Right. And sort of they stick together, so what's the final velocity vector? Like which way is it going and how fast? So the way we do this, we split it into components. So I'm going to find the initial total momentum, but I'm going to do it twice. I'm going to find the total x momentum and the initial total y momentum. Right? So what is the initial total x momentum? Well, first of all, I have to define what I mean by x and y. Or like what are my, it's like a coordinate system here. And I think I'm just going to go with sort of common x is this way, y is this way. Note it doesn't really matter where I put the origin of my coordinate system, because really what we're looking at is just like a collision at a single sort of instant in time. Right? And we're just comparing velocity vectors. So I really just care about the directions. What is x and what is y? Okay, so x is to the right or east, whatever that corresponds to. So what momentum do I have? Let's label those. This is block A and this is block B. Right, so I've got ma, the mass of A, times the velocity of A, but in the x direction, the x component of the velocity, plus the mass of block B times the velocity of B in the x direction. And that's going to be equal to the final total x momentum Now in this case I only have one final object, so what should we call this? I'm just call it maybe capital M, that is its mass. This has velocity, just v, I guess we call it, no subscripts, v in the x direction. And then those are going to be equal because of momentum conservation. So this is mass m. Of course know what that is because it's 5 kilograms and 3 kilograms. So that's going to be 8 kilograms. Okay, so now I can solve this for this. So the x momentum conservation, the initial total x momentum is the final total x momentum. That's going to give me, in this case, the x component of the final velocity. So I'm just going to solve this. I'm going to have vx is equal to ma, let me write it out, vax plus mb vbx, so the x component of the velocity of v, and divide by m, the total mass, because just to arrange this equation, to isolate this. Now what are those? Well, A is going all in the x direction. It's going to the right, so that is just 3. So I'm going to have 5 kilograms times 3 meters per second. Then what about this one here? Well, this one, the velocity vector is going to the right and up, so I have to take components, right? It has a component that's sideways and a component that's up and down on the page. Now, what component is what? You know how to take components of vectors. But if I take components like this, right, then I want this part here, and it's the opposite of this angle, so it's going to be sine. So I'm going to have 3 kilograms, the mass, times the x component of this, which is 4 meters per second, times sine of 30 degrees. Divide all of this by 8 kilograms. Then we can solve it. So I guess it's going to be 15. Now sine of 30 is exactly a half. So 15 plus, I guess let me write out, 15 kilograms per second plus 6 kilogram meters per second, right? Because 3 times 4 times a half divided by 8 kilograms is going to be, notice the units match, kilogram meters per second divided by kilograms, leaves me with meters per second, 21 over 8, which I think is 2.625 meters per second. So what I found, what is this, is the x component of the final velocity. It's positive, so another thing is going to the right. Figured out how much it's going to the right. I haven't figured out yet whether it's going up or down or something else. So let's do the y momentum next. Of course, we set this up exactly the same way. So I guess we say initial y momentum. And I mean the total. Like I said, total here, should have said total in here too. That's ma times the y component of the a velocity plus the mass of b times the y component of the, sorry, I'm doing b, of the b velocity, and that's equal to the final total momentum. Of course, final, in the end, there's only one object. So that's equal to the combined mass of the combined blob times its y velocity. Don't know what it is. That's the thing I can find. Let's solve it. I'm going to get Vy is equal to, well, ma Vay plus mb vby divided by m. Now what are those values? Well, a is not going up or down at all in the y direction, so that is 0. This one is 0. So actually it makes it rather simple. Need to find this, and we write it here, so it's 3 kilograms. That's the mass of B. You see it up here. Now I want the y component of this, so that's cosine 30. 4 meters per second times cosine of 30 degrees divided by 8 kilograms. And if you plug in those values and you work it out, I think what you're going to end up with is approximately, you get your calculator out for cosine 30, approximately 1.3 meters per second. So we have the x component, we've got a y component. Let's draw this quickly in a picture. My final blob, put down what's the end result. With one blob, 8 kilograms, and it has an x component of 2.65, that's to the right, because it's positive. And the y component of 1.3, so that's up, but not by quite as much. It's about half. So the overall velocity vector is going to look something like this. Now how do I find the magnitude? Well, I mean, I just express in components, right? Vx is 2.625 meters per second. Vy is 1.3 thereabouts meters per second. So then you can find, of course, the speed, like the magnitude of the velocity, just by using Pythagoras, Vx squared plus Vy squared. I leave that to you to just plug in the values. And if I want to find out, say, what's the angle here, well, again, I can just use the geometry of vectors. And if this is angle theta, then I'd say that tan theta is opposite over adjacent. So that would be Vy over Vx. Of course, don't just sort of look at this and put it in your equation bank and then pull it out whenever it looks right. No, think about your geometry, right? Don't think this always applies. What angle do you want? What sides do you have? You know how to deal with vectors. So do it yourself and think about it every time you do it. Just emphasizing that, because often enough I've seen, in an exam, somebody using, pulling out some sort of equation that applies to a situation where like another angle was known. It's similar but not the same, and that just tells me, look, you've just sort of maybe learned some equations off by heart, or you don't really understand where it comes from, how to construct it. So make sure you understand why it is this one, not sine or cosine, or how could I find this angle with sine or cosine instead. You should all know all of this, right? Because you've dealt with vectors before, with velocity vectors, force vectors, and so on. Just a good place to pause and emphasize this once again, right? Don't try to think of this as an equation to remember. Goodness no, right? Understand the geometry of triangles. That's how you get it right every time. Alright, let's go to the next example. So here's the next example, our second or last one. It's going to take us a little while, I suppose, to actually solve this. Here we've got two identical particles, and I'm not saying these are fundamental particles or something. Whatever they are, right? It doesn't really matter. Two particles, they collide, and they collide as shown. And then they break, one of them breaks into two equal pieces, sort of shown here. Now, I doubt there'll be a physical process where it actually looks exactly like that. But we can pretend there is, right? It doesn't matter how I've drawn it. So notice it doesn't tell us what the masses are. I'm going to find the final velocity. Well, let's give the masses a name, right? Let's say this is mass m. M for mass. Mass m. Well, this one's going to have mass m. Each of those is going to have mass half m, or m over 2, m over 2. Because it's half equal pieces. Okay, so notice that I've got a lot of vectors here. I've got those two initial ones, and then I've got two final ones given, and the third one I have to find. Right, I have to find both the sideways component, let's call it this the x direction, and the up or down component, let's call it the y direction. Now, can we get an intuition? Well, this one's going to the right, this one's going left. This one's going a little bit left, but fairly slowly. It's not really sure. It's going to go left or right. I don't really know. How about up or down? Do you know if this last piece is going to go up or down? Well, this one's going up initially, fairly fast actually. But they're both going up. So is there like momentum upwards, momentum left over or down? I don't know. So let's leave it open. I can interpret the sign of my final answer as giving me the direction, right? If it's positive x, it means it's going this way. Negative x would be going this way. Same with the y. Positive y, negative y. I don't know the answer in advance. But I can solve this systematically. So, initially, I'm just going to write initial x momentum, and I'm going to put the final x momentum here, and then I do the same thing with the y. So again, we solve x and we solve y separately. We don't mix them. The only time you might mix them is to calculate, say, the final length of your final vector. Right? Like the magnitude or the angle. But not when you do any of the momentum conservation equations. Like this does not make sense. Like there should be no equation where you combine them unless it's purely to solve something algebraic. Okay. So what is my initial x momentum? Well, it's m. I don't know what m is, I don't have a value for it, but that's okay. Times 500. I'm not going to write meters per second, I'm going to leave the units implicit, they're all meters per second. So don't anticipate any difficulty, and if I write m per s, I might get confused with my mass m. So I'm going to make the conscious choice here to leave the units explicit, because everything is going to be in meters per second. Okay, then I'm going to add the x momentum of this one. Of course, this one I have to take the components. Now, it is going to be 1000 sine 45, but it's going left, so it's minus m times 1000 times sine 45. Right, notice I can see it, that it's going to be negative, right? I'm not going to worry about, oh, I measured the angle maybe from like this direction, and 135 degrees, is it sine positive or negative? It's going to get you into trouble. Just look at it. You know which way it points. It's the negative x direction. Minus. Deal with the angles that are simple, that are small. Why make your life more complicated because somebody online told you to go to start here and measure this angle? Nonsense. You're just going to get yourself into trouble. Alright. So sine 45 is 1 over root 2. So I'm going to simplify this. I'm going to have m. And then it's going to be 500 minus, and this is about 707. So, interestingly, this is in fact negative. Right, it's minus 207 m. Okay, so the overall momentum of the system, this combined system, is negative, right? It's going more left than right, well, because this one's going a lot faster than this one, even though it's at an angle, it's still going faster left than this one is going right. Okay, so negative overall momentum, that's not a problem. We don't care. Let's figure out the final one. So what am I doing? The final x momentum. I hope you caught that. Luckily for me, I caught it before I actually got started. So I've got 3 pieces here to take care of, so I'm going to include them all. I've got this one here, so I'm going to write m times 600, right? No. This is momentum. This is velocity straight up. That's not the x direction. So it's m times 0. Then I've got 1/2 m, that's this piece here, times, so it's going left, so it's a little bit of a minus there. The speed is 100. I want the horizontal direction is the opposite of this angle, right? Because imagine drawing it like this. This is small because it's low velocity. Like this would be the y component, this would be the x component. And this, of course, is my actual vector, right? The angle is 30, it's the opposite, 100 sine 30 degrees. And then there's the unknown one, so plus 1/2 m. I have no clue. Call it Vx, it's part of what we're trying to find. This one goes away, and sine 30 is, again, it's just half. So I can simplify this to be 1/2 times minus 50, so minus 25 m plus 1/2 m Vx. And now those two, they are going to be equal. So I have, that's by momentum conservation, right? Total momentum, momenta are equal. Total x momentum initially equal to total x momentum at the end. Okay, so we can cancel out the m's, all of them, right? Because it appears in every term. And now I can actually see that, look, this is a lot bigger a value than this. So it's going to be minus 182, cancel the m's, equal to 1/2 Vx. And so I find that Vx, oops, what am I writing? Vx is equal to minus twice this. I think it makes 364. Of course, it's in meters per second, because everything has been in meters per second. So negative, it's going left. Notice here I had 3 pieces making up the final momentum, because the 3 pieces here I have to include all of them in my calculation. Okay, now we do the same thing with the y momentum. We do it like this, so I can just keep the diagram up. So the initial y momentum, and of course I mean the total, right? Not just of one piece, but of all the pieces. What is it? Well, it's going to be m times 500. No, wrong. This is in the x direction. It's m times 0. This one's not going up or down at all. Always make sure you're working in the right direction. It's so tempting to just sort of quickly, oh yeah, 500, put in a number. Okay, right now I'm working this way, vertically. Okay, this one is not moving vertically. It can have 1,000,000 meters per second to the right. I don't care. It has 0 momentum in the y direction. This one here is going up, so it's going to have m times 1000 times cosine 45, because I want this component here, although with 45 sine and cosine are the same. So this one actually also comes to 707 times m for my momentum, m being the mass. My final y momentum. Well, again, I've got 3 pieces to worry about, and actually both pieces now have an upward component. So I'm going to start with this one here, m times 600, plus this one here, so the mass of it is m over 2. Right? Just because you remember momentum is m times v, well, that doesn't mean I plug in this, like the m I'm using here for the mass of the particle. The mass of this thing is m over 2, because m was the mass of this. This is half of it. So that's what I plug in into momentum. Times 100 times cosine of 30 degrees. Right, I want the vertical component. And then I add to that the unknown final y velocity of this last piece. Its mass being m over 2, and again, it could be positive or negative, I don't know until I've actually evaluated it. Okay, so this is going to be m times 600, and then plus, let me check, I think it comes to 43.3 m. So that's 100 times cosine 30, which is about 0.86 over 2. Is that right? I've forgotten this one for one. Okay, where's the mistake? The mistake is that this one here, no, actually, sorry, I'm totally confused. I was going to say it's going left, it's negative, but see what I'm doing? I'm confusing x and y. No, this is correct. It's going in a positive y direction. I was about to say, hey, there's a mistake here. I made a mistake. Look at me. It should be a minus sign, but no. I confused myself here. But by doing this, this is going upwards. It's in a positive y direction. What this one had was a negative x component. So back here, I had a negative value. Alright, again, lucky I caught it right now and not after doing all the algebra. So now I can set those to equal, and I can solve for the final y velocity. So, again, they're equal because of momentum conservation. So I've got 707 m. So my y momentum initially. And here it's going to be m times, I guess, 643.3 plus this unknown piece, 1/2 mvy. And I can again cancel out the m because it's in every term, so it doesn't matter what the mass is. All that matters is those are of equal mass, and these ones are half of the original each. Right? The final velocity does not depend on what the actual mass is. Is it 1 kilogram? Is it 1 microgram? Is it 6 tons? I don't care. Okay. So now let's see if we can solve this. So I'm going to simplify this. 707 minus 643.3. See if I can do this. It's going to be 63.7. And that's equal to 1/2 Vy. And so that means the y velocity of the last piece is going to be, well, twice this. So that is 127.4, and everything was in meters per second. Notice it's positive, so it's going up. Upwards on the page, whatever that refers to in real life. Maybe it's north, maybe it's south, maybe, I'm holding this map upside down, if you like. Doesn't matter. But as drawn on the page, it means the momentum is going upwards, the velocity is up. Let's draw the final result. So here's my last piece, right? The unknown piece. This one here. And what did I find? I found that it was going minus 364 in the x direction and plus 107.4 in the y direction. So it's the negative x by quite a lot, 364, and 127 in the upwards direction. It looks something like this. So I can draw my vector roughly like this. So this is 127.4, and this is 3. What is it? What was it? Minus 364. So 364 is what's going to go here. Now I leave it to you to figure out what's the magnitude and what is the angle. How about you find this angle? Again, think carefully about the geometry, which side over which side, is it tan, cosine, sine. There's more than one way of doing it, especially once you found the magnitude. Just make sure you can still do that. Am I going to give you the answer? No, because I haven't worked it out myself. I don't know what it is. But just good practice to keep those basic skills going. Anyway, I hope this helped to talk a little bit about the two-dimensional case, so you can apply those techniques to your own two-dimensional momentum problems. And of course, you can generalize it to more than 2 dimensions simply by having another heading that says initial z component or z component and final z component or z component, depending what country you're in. And if you've got 4, 5, 6, 7, 8 dimension, well, you just keep going. Of course, you can't draw it on the page anymore, but so what? The maths and physics still work out. Alright, thank you for watching, and I'll see you in the next lecture, where we'll start to talk about energy, another conservation law.